Giving a talk later in August or September. Tonight's talk is Life Near a Black Hole by Dr. Ed Friedman. Ed and I have known and argued with each other for 35 years. He has an undergraduate degree from University of Maryland and a PhD from Wayne State University. He spent pretty much his entire career, he's done a few other things, but pretty much in electro-optics and science and astronomy, especially electro-optics for science. He's worked for Lockheed Martin in Denver, which is where we met. He's worked for Ball Aerospace and Boeing, and has worked on a lot of the science missions that you hear about on the news for NASA. So with that, let me turn it over to Ed.
All right, thanks, John. So tonight, we're going to talk about what happens if you venture close to a black hole. There are a number of challenging concepts involved, but stick with me. I've taught this many times, and I think we can get through it together. I'm going to emphasize the results of a very interesting way to visualize what happens near a black hole. So even if I lose you on the technique that we use, don't give up, because I will, as I say, I will keep repeating the results of our analysis. And the fantastic thing about this lecture is there's no math. We can get the results that all of us are interested in without doing math. So to do this, hang on. First, let me tell you what we're going to accomplish. We're going to use graphical techniques to look at what cosmologists call causality near black holes. What happens if I do this and somebody else does something else? How do we affect each other? But we can do this without messing with the math. And we're going to have two explorers, Alice and Bob. I should tell you a little bit about their backgrounds. Alice, obviously female astronaut, extremely brave and adventurous. And Bob is like me. He's going to hang back and watch what happens because he's a little bit timid. Here's Alice. Here's Bob. Occasionally they will appear in rockets. You'll see why in a few minutes. And we're going to answer some questions. What does Bob, the timid one, see when Alice approaches a black hole and decides to cross the horizon of the hole? And I will define what a horizon is shortly. And what does Alice experience when she enters, goes through the horizon and enters the black hole? And what happens when they send messages to each other? Now, these messages will all be sent by electromagnetic waves at the speed of light. But things happen as Alice approaches the black hole. And we'll also look at what happens if they both enter the black hole. And by entering the black hole, I mean they both cross the horizon. But once again, I will define what a horizon is. So before we really get into this, we have to talk about world lines. And principally, we're talking about mapping. So here's a map of the neighborhood I live in. Here's Boulder, Colorado. And there's a pretty much straight road to the town of Longmont and Niwat's in between. And this map is very useful if you've never been to the neighborhood, but it does not include one critical thing we have to consider when we do black hole physics, and that is it doesn't include time. And one way that we can get rid of or overcome that limitation is to draw a different kind of map. And that map looks like this. It's traditional for cosmologists and relativists to draw time in an upward direction and one dimension of space horizontal. Yeah. So here's the same map, Boulder, Longmont, and Niwot in between, and any traffic that goes on between these will be represented by a tilted line that takes into account time, because here we have Tuesday, Wednesday, Thursday, Friday, and so forth. So let me give you some examples. First of all, a vertical line means nothing is moving. The town of Boulder doesn't, on this map, the town of Boulder does not move. And yet it has a arrow, a directional arrow, because time carries it upward on this graph. Same with Niwot and Longmont. So we're going to redraw this, and we're going to change the units. Let me back up and just say, we could have, here I picked the units of days. That won't be helpful when we're talking about black holes. A much more appropriate set of units are time, we will use seconds, and distance, not measured in miles or kilometers, but light seconds. And so here's our grid. These are horizontal lines represent constant time. Vertical lines represent position. And here's how your world line, your travel, is depicted on this map. If you drive a car from Boulder to Longmont, it might take you 5 minutes or something like 300 seconds. If you decide to go faster and you use a rocket, your trajectory on this map will tilt to be less vertical because you will achieve the distance you want in fewer seconds. And if you send a light beam, either to Longmont or from Longmont, and you use these units of seconds and light seconds, a light beam will be at 45 degrees. Because in 1 second, let's say this is 1 second, light will propagate 1 light second by definition. So in order to use this mapping approach, we pick these kinds of units: time in seconds, distance in light seconds. And we're very interested in, because we're going to be talking about communication between Alice and Bob, we're very interested in lines that are drawn at 45 degrees, because those represent the fastest we can communicate between astronauts. If you try to draw this line, it represents speed faster than the speed of light. And that's disallowed. So we put the international symbol of don't go there for this line. So everything that happens, if you're in Boulder and you're thinking about traveling to or communicating with Longmont, everything happens in this arc of 45 degrees. Now we can make this a little more general. Of course, we only have 2 dimensions to work with on the screen, but here's our distance scale and here's our time scale vertically. And we can kind of simulate a second dimensional scale this way by drawing cones. And these are called light cones. So if you're here now, your entire future is defined by this cone. And everything that describes you here now came from this light cone in the past. Nothing that influenced your position or your DNA could have come from any place but this light cone. So I've said these things. Yeah, we got to do some muting because I'm hearing confusing noise in the background.
Looks like Brent is.
Yeah, you think, right?
Yeah, yes, can everybody please mute other than Ed?
Okay, thanks. All right, so key thing here is, right here, we are looking at what cosmologists call flat space-time. That is, there's no mass around to influence the shape of this mysterious thing called space-time, which we will describe in more detail shortly. So this is what life would look like, a flat space-time where you have a light cone in the past and the future. Now we're going to add matter or energy. And remember, they're the same thing according to E equals mc squared. Matter and energy are interchangeable, and I will probably use both terms during our talk tonight. And when you add matter, that flat space-time, for example, this could have been the map that we drew describing the neighborhood of Boulder and Longmont. If you add a mass, things like this happen. Frequently, the way people depict this is to imagine this is a trampoline and you put a bowling ball on the trampoline, you get a big dent. If you put a golf ball on, you get a dent, but smaller. And so the presence of matter or energy distorts the space-time that we were talking about in the map I just showed. And we have to be able to deal with that because a black hole has lots of matter, lots of energy, and it distorts space-time dramatically. So here's a three-dimensional grid, which we can try to use to depict the space-time continuum that Einstein introduced back in 1915 through 1917. And here's what it looks like when you add matter to it. All sorts of distortion in the shape of space-time. And I'm using that's one word, space-time, linked together, meaning that not only is space influenced by the presence of matter or energy, but how time progresses in that neighborhood is also affected. And we'll see this played out in great detail. So in reality, according to this Einstein's theory, Newton's law of gravity really is a fiction. There is no such thing as gravity. The reason objects are drawn together, such as Earth and the moon, is each of them influences space-time. It puts a dent in the three-dimensional space and four-dimensional space-time around each body, and that's what produces the effects that we see and use to fly to the planets and so forth. Fortunately for us, Newton found a very simple formula that is still used today to calculate trajectories of spacecraft going to the other planets and so forth. But if you use Einstein's theory of gravity, once again introduced between 1915 and 1919, you can derive Newton's law of gravity. So the fundamental thing is Einstein's theory of gravity. And so we say there's no such thing as gravity. And here's another depiction of the dent in space-time caused by our sun. Not only does it affect the trajectory of the planets and everything around it, but also deflects light. And this has been proven over and over again in a wide variety of experiments. We know Einstein was right. In fact, the famous physicist John Wheeler gives us this wonderful quote that space-time tells matter how to move, and matter tells space-time how to curve. So they are shaking hands all the time. And so now we're going to deal with the questions related to being near a large massive body like a black hole, and our ability to use a conventional map, such as this globe, the sphere of Earth. We have to prepare our minds for distortions in what we would normally expect when we build maps. And I'm just going to use this as an example. Here's the globe we're all familiar with. Here's a flattened version of the globe, a projection that gets the whole globe onto a two-dimensional surface. But I want you to notice the size of Greenland and the size of Australia. And to flatten our globe requires a substantial distortion. And I've copied those two islands so you can see them from that flattened map. Here's how the relative size of Greenland and Australia. In reality, that's their relative size. So I want you to prepare your mind for distortions related to maps because of the curvature of space-time. Without that, we can't really talk about the adventures of Alice and Bob. So let's talk about what a black hole is. As matter aggregates, for example, if a big star collapses and the matter falls to a smaller and smaller volume, a thing called a horizon can form. And I'm going to illustrate in a second what that looks like. And a horizon represents a boundary around the object that forms when a giant star collapses. The horizon is more or less like the boundary between Kansas and Oklahoma. It's just a place. Nothing terrible happens when you arrive at that place, but it has significant impact on your ability to control your future. So as a big star collapses, matter falls altogether into a singular point called the singularity, It's a location where all the laws of physics disappear. And how big is a singularity? Well, it's the smallest thing in the universe. So I'll give you an example. There's a black hole at the center of our galaxy. It contains the equivalent of 4 million suns, and it is invisibly small. It's smaller than an atom. It's smaller than an electron. It's the smallest thing in the universe. And all of that energy, all the E equals mc squared of 4 million suns has fallen into that point. And you might wonder, well, where did the energy go? It went into bending space-time. I'll show you an equation that describes that. We're not going to do math, but just because it's like a piece of art, you have to look at that. So all the energy that falls into the black hole is invested in bending space-time. And we end up with a singularity, and around it is a spherical surface we call the horizon. And black holes are extremely simple. Now, I'm simplifying for some reasons. Later in this lecture series, we can talk about what really happens around black holes. But a simple black hole has 3 properties. It has mass, it has electric charge, and it may have some rotational property. But it's the tiniest thing in the universe. And as I said, the horizon's not a physical barrier. It's just a boundary, but it has enormous significance if you go near the black hole, as Alice will do. So here's a depiction, kind of like a trampoline thing, where you dropped a very heavy bowling ball in the trampoline and distorted the space-time around it, and the horizon looks like that. And so, like I said, sometime in the future, I can give a lecture on the formation of black holes. So here's a way to think about horizons, because you must understand horizons to follow what we're doing. So here's a beautiful day on the lake. Guys are out fishing now. Some evil genius drills a hole in the bottom of the lake. So water is rushing down that hole. And if he drilled the hole way over there near the shore, these guys would not even notice. But if they're near the hole and water is flowing down the hole, they're going to notice their boat start moving, kind of like this. Here's the hole the evil genius drilled, and water is flowing down that hole. And there is a speed limit for their boat. They can only go, say, 20 miles an hour. At some distance from this hole, the water is flowing at 20 miles an hour. And that's this circle that I've drawn here. That depicts the area or the place where the water is flowing at 20 miles an hour. If they're outside that ring, they can putt and go away and survive. But if their boat is inside that ring and they can only go 20 miles an hour, they can never get out and they will be lost down this hole. And this is what happens around a black hole. And the horizon is the place where light cannot escape from the black hole. Now, there's an additional complexity to this, of course. A collapsed star is in a spherical 3-dimensional space. So everything I've depicted here is kind of 2-dimensional. The surface of the horizon of a black hole is a sphere. Now, this I've already said. What we're going to now do is challenging, but hang on. I will try to be very careful. If you don't understand it, it's my fault, not yours. But we'll do the best we can. Okay, so here are Alice and Bob. And you notice Alice is in Boulder, Bob is in Longmont. And when they send messages, and first of all, neither one of them are moving. And light rays on this map is like the map we showed earlier. Light rays go at 45 degrees. And so here's Alice not moving. And here's Bob not moving. And they can send messages like this. She sends him a message, he sends her a message. And they can send messages back and forth. Each one of them has a light cone. Their physical person has to stay in this light cone, and the fastest they can send communication is along this 45-degree angle. And Bob has his own light cones. Now, let us introduce mass to Alice and Bob. So And we need a tool to do this. We need a way to depict what happens to them. And we want to be able to depict flat space-time, like we started with, curved space-time due to the influence of mass or energy. We want to include the horizon. We want to include the singularity. We want to be able to cover all of space and time, from ancient past time to far future time and all of space. And we want a depiction that maintains this idea that light rays move on diagonals. And in the process of doing this, we will be duplicating the effects of Einstein's very famous equation that shows curvature and its relationship to energy. That's what this does. But we don't want to get into this math because it looks like this. It's actually worse than this. This is just an example. So we have a product invented by a student in the 1950s named Kruskal. And Kruskal studied this problem and decided to use distorted maps to produce a tool for understanding how things behave near black holes. So here's our singularity. Right there's a little dot, and there's the horizon. And this is time and distance, just like the first maps I showed you. But what happens to light rays? A light ray that approaches the hole doesn't stay in one place. It's distorted. It gets bent. And this has been proven using eclipses for over and over since the early 20th century. If you're far away from the hole, you never notice the influence of the warped space-time here. And we're going to number these 4 rays because we want to see how they look on the Kruskal diagram. This is the Kruskal diagram. I'm going to show you what it means. First thing we do is we cover up this half. In another lecture, I can talk to you about what that half is thought to mean. This triangle right here is our universe. Everything we know and love is in this space. The future is here. The past is here, just like in the first map I showed you. And here's curve 1, 2, 3, and 4. These curved lines represent unmoving objects. So if you're in the past and you're at this position, this line called 2, and you don't do anything, and you somehow maintain your position near a black hole, you stay on this curve from past to future, just like that. If you're far from the hole, your trajectory follows curve number 4. Now, let's try to understand where is the horizon on this distorted Kruskal diagram. This dotted line is the horizon. So the sphere that's around a black hole on this map becomes a straight line. And there it is. This is the horizon. Where is the singularity? Oh, first of all, there's this. The singularity is this arch with dragon's teeth telling us that the point at the center of the black hole where you will certainly die actually turns into this curved line. So once again, distortion is an inevitable result of trying to visualize what happens around black holes. Lots of distortion because the point at the center of the black hole, that is the singularity, it becomes a curved line. The sphere around the black hole, the horizon, becomes a straight line. Trajectories are curved. And let me show you how time works on this. Oh, yeah, I can do a future talk about what's behind the blue triangle. This line is constant time, sometime in the past. And in fact, this line, this one I'm trying to depict with my cursor, that's the infinite past. So long ago, past is somewhere along this line. So we have a mesh of time and space, just like we had when I showed you a map of Boulder and Longmont, except this one is distorted. And as time goes on, the blue lines sweep upward like a windshield wiper effect. And far, far in the future, the horizon, this line, the horizon is coincident with infinite future time. This is the most complicated drawing in this presentation. So the infinite past is along this line, the infinite future is along this line, and the infinite future and the horizon coincide. And you'll see why that's helpful here in a second. Here's a better drawing of the Kruskal diagram. Don't worry about what's written on there. That's not important. So what we have done, or what Kruskal did, is he took this map, the original one I showed you of, Boulder, Longmont, and time, everything is flat and linear, and he turned it into this monstrosity, but it captures everything we need. Light rays go at 45-degree angles. There's a horizon, which coincides with this. Light cones are preserved. That means light goes at 45-degree angles, and all of time is captured from minus infinity time to future infinity. And straight lines, these straight lines, this line here is a straight line. Anything along that line everybody on that line is at the same time. So back in the ancient past, there's dinosaurs, and there's the Roman Empire, there's modern America, there's the far future. So our Kruskal diagram, which also I'll remind you includes this line, which is the horizon, and the dragon's teeth is the singularity where everything is crushed to zero volume. It's not a good place to be. There's a horizon. So now let's talk about our first experience using the Kruskal diagram and Alice and Bob. So remember, anything along a straight line is at the same time. So at any one time, let's say 6 months ago, Alice and Bob are different distances from the horizon. This is the horizon, because they're on different curved lines. The curved line is a position. This curved line is a different position, and nobody's moving, but they're near a black hole. So how do they avoid moving? Because this is a gigantic gravitational body, and the answer is they have rockets, and they stay hovering above the black hole. Or they can orbit. It's easier to visualize if you just think of them above the black hole using a rocket to stay levitated at a constant position. So here's Alice and here's Bob at one time. Later in time, here they are. Nobody has moved. And here they are at some later time. So everything's a little distorted, but I think by now you see how this works. So Alice is on this curved trajectory, and Bob's on this curved trajectory. It's similar to what we saw earlier in this talk, where they were in a flat space-time that did not have a horizon. Alice and Bob both were traveling on straight trajectories. Now everything is distorted. So now we're going to get more involved. Here's a light cone. I have to get rid of the little thing with the people. Here's a light cone for Alice. Alice is here, and everything she does is confined to this cone. That's her future. She has to be very careful if she picks a trajectory that deviates from the one she's on. See, this is the one she's on. And if she has a rocket with infinite amount of fuel, she can safely fly, just hover above the horizon, which is the green dashed line. But if she turns off her engine here, for example, gravity will draw her toward the horizon. And once she passes through the horizon, I'll show you what happens. So there's her light cone if she stays outside. If she sends a light ray outward, out toward Bob, it has this trajectory because it's a 45-degree angle. That's the speed of light, is represented by a 45-degree angle. If she sends a light ray inward, it goes through the horizon and hits the singularity and is lost from the universe. Inward and outward light rays. Now, what happens if she's inside? Any light ray she sends from inside, from any place in this area that's up above the horizon, her light rays immediately go to the singularity. If she tries to...
This is John. Can you explain to people the singularity? Is that the Schwarzschild radius? Is that the hemisphere of a black hole?
Okay. The Schwarzschild radius is the location of this line. It's the distance from the singularity to the horizon. So for those of you who are familiar with the terminology, there is a distance called the Schwarzschild radius, and it's the distance between the singularity and the horizon. So here's the point though. Everything that Alice does is confined to this cone. And if she decides, or once she's inside, you can see there's no trajectory. You can place this hourglass thing anywhere in here, and her future is the singularity. She is doomed. Outside, if she has a sufficiently strong rocket, she can stay outside forever. But once she crosses this green line, she's doomed. There's no path forward for her that does not intercept the dragon's teeth. Okay? Now, let's do some communication like I showed you before. In a flat space-time, here is Alice and Bob. If they don't move, so keep in mind, so far, no one has moved. Alice and Bob aren't moving. She can send a light signal to him and he responds and so forth. Things are different here near the black hole. So I hope you noticed that. Let me do it again. Right here, Alice is going to send a message to Bob. It's a blue line. Did you see that? And he responds. And she responds, and he responds, and so forth. So they're having a conversation, and so far nobody's moved because they both have rockets, and they're being very careful to stay outside of the horizon, which means they stay in this quadrant, which is the universe we all live in. Now, this is a reminder to me, and I'm right on schedule. It's going to take me 25 minutes to demonstrate a series of experiments we're going to do with Alice and Bob using the Kruskal diagram. So once again, the Kruskal diagram. And this is an animation that we can talk about for a second. It illustrates something very odd and bizarre, that if an object crosses the horizon, which is this, should have a green line there, but you know what this is. Anything that crosses the horizon has its spatial and temporal coordinates swapped. This is what the math says, and this is what illustrates it. If you're coming in closer, remember a curved line here represents position. So this curved line is coming close to the horizon. Once it comes in, it turns into a line that's going upward, and the future of that line is the singularity. So this is another way to say anything, light, matter, energy of any kind that crosses the horizon, which is this straight line right here, anything that crosses that horizon is doomed to end up in the singularity and disappear from the universe. And that's scary. Inside the horizon, between the horizon and the singularity, your future is not a time, it's a place. Those of you with some math background could, if you want to contact me, we could talk about what that looks like in the math. It involves imaginary numbers. Nobody understood this, by the way. From Einstein's invention of relativity in 1917 until sort of the mid-60s, none of this was understood. The people kept seeing odd things happening in the math, and the idea that it was describing an object like the one I'm telling you about was not in the vocabulary of physics until the late 60s and early 70s. This is recent stuff. Okay, so let's carry on. Here are Alice and Bob. I've given Bob a little rocket. Alice has her own little jetpack. Here's the horizon. Remember, it's a sphere. Here's the singularity, the smallest thing in the universe, and they're hovering. They're not moving. If they shut off their rocket, they will fall toward the singularity. And everything I'm going to describe to you involves them moving what I call radially. That is, in the experiments, Alice is going to shut off her rocket, and she's going to drift toward the singularity. There's other ways to do this where they are actually in orbit. If you've seen the movie Interstellar, which was produced by Kip Thorne, one of the great gravitational physicists alive today, everything involves orbits, but here we're doing radial motion. Okay, let's get busy. So here are Alice and Bob on the Kruskal diagram, and they're communicating with light beams and hovering above the horizon. That's what this depicts, and they're not moving, right? Alice is going to, I told you already, she's brave. She's going to shut off her rocket because she wants to explore this space, which is the volume between the horizon and the singularity. And we're going to see what happens to her. There's several questions appearing over here. What happens when she crosses the horizon? What does Bob see? What happens to Alice? And so forth. And I can give a future lecture on the real environments around black holes, but we're not going to do that tonight. Okay. So the first thing that happens is Alice and Bob agree that she is going to send light signals to Bob, kind of like this. Remember, straight lines represent time. So some past time, she sends him a signal. She sends him another signal. She sends him another signal, and so forth. He responds. Here's an example, again, of his response. He sends her a signal. So if he sends a signal at this point in space-time, she gets it here. So we don't need to talk about that. Now, so far, once again, even though Alice has announced she's going to sacrifice herself and fly through the horizon, she has not yet moved. But she's going to move now. So Alice is going to shut off her rocket. But before she does, she and Bob agree she's going to send messages every second. It's a form of clock. She's going to send a message. I am fine. I had breakfast cereal and stuff. Every second, she sends him a message. There's the first message. There's the next message. And the next. And the next. Now, this one's significant because right here, look at the time. Now, these times are arbitrary. Just know that anytime you get close to this line or this line, the time is very far in the future or very far in the past. So what I'm saying here is at time t equals minus 50, remember there's the time as a straight line, t equals minus 50, right there, she sends a signal and Bob gets it at, I'm saying, an arbitrary time, t equals plus 10. So 60 seconds have elapsed, right? 60-second time delay means he's 60 light seconds above her, hovering over the black hole. Now, what happens when she sends a signal from her message sent at t equals minus 10? So remember, this is her trajectory. This is her line. So right here at t equals minus 10, there's t equals minus 10. Right there, she's going to send a signal to Bob. When does he get that? He gets it at t equals 500. T equals 500 is not 60 seconds later. It's 510 seconds later. Now, why did that happen? It's because space-time, particularly the time part of space-time, is dramatically distorted for objects closer to the massive object than those farther away. Time slows down. Bob, what does Bob conclude from this? Well, I'm supposed to get a message every second. But this message I haven't heard from her for 510 seconds. What's going on? It's because she's about to fall into the black hole across the horizon. How about if she sends a message here at t equals 10 seconds? Oh, and well, let's stop for a second to make sure everybody understands. Whose time is this? This is the time of a distant observer watching this happen. Because Alice's clock rate relative to the universe is changing dramatically because of the influence of the black hole. Bob is, at least initially, confused. Why is her clock slowing down? Eventually he goes and reads Einstein and he realizes, oh, it's because she's closer to the mass of the black hole than I am. So now when does Bob get this signal, the one at t equals 10? Remember, the closer you get to this line, the closer you are to time infinite future. This signal, this orange line, he might not get that for thousands of years. Years of time delay. And then how about if she sends a message just at the horizon? Well, since the horizon and t equal infinity are the same line, he will never get that message. Here, this red line represents a signal she sends to him as she crosses the horizon. He never gets that signal. He could wait billions of years and he will never see it. What does he conclude? He concludes that her clock has stopped because she promised him she was going to send a clock signal every second. And now it's taking hours or years or maybe billions of years to get a signal. So her clock must have slowed down dramatically. And indeed, that's exactly what happens. Now, what does she experience during this? Her wristwatch keeps ticking away just as like normal. Nothing changes for her, leaving out some details. So her clock seems to be slowing. And what happens if she's inside the horizon, represented by the green line? If she's in there and she sends a signal in the direction of Bob, remember he's above her, radially above her, no signal she sends ends up anywhere but in the singularity. This is what I meant by saying that once you're inside the horizon, your future is not a time, it's a place. Any signal she sends collides with the singularity, which means an outward bound light signal actually goes downward and hits the singularity. He never gets that message. And that's the key feature of black holes. Nothing comes out through the horizon. Now, what have we got going on? He never sees her cross the horizon, even if he waits an infinite amount of time. It appears like she freezes on the horizon. Now, there's some technical things I'll discuss very briefly, but that's kind of disturbing. The technical reason is that her light is redshifted. We don't have to go into the details. You can write to me separately if you want to talk about that. She kind of just fades away, but it appears like she's just going to land on the surface of the horizon and never enter the hole. And of course, he never hears from her again. But her clock keeps ticking away just fine. Now, let's talk about her shape as this happens. She gets squashed. Think about this. Imagine a long stick instead of Alice. And the long stick is falling toward the horizon. The part of the stick closest to the black hole appears to stop on the horizon, but the piece of the stick farthest away could still be moving. So essentially, it looks like all the matter made up by Alice just gets squished and flattened right onto the surface of the hole. Anyone seeing this and watching stuff fall into the black hole sees the same thing. It all just piles up on the surface. But actually, the stuff from the point of view of infalling material, no such effect occurs. They just fall through the horizon, like going from Kansas to Oklahoma, and they're doomed. They know this ahead of time. Okay, we've said all these things. Now, how about when she's inside the hole? Remember, she decided right here, she's going to enter the black hole, and nothing terrible happens even until she gets inside, where she could live for a while. I'll show you some examples in a minute. Bob is sending her messages. You know, he's on this trajectory. And he sent her a message here, and she'll get that message. And he sent her another message here, and she'll get that message after she crosses the horizon. And this is the last message he can send that she will get before she's swallowed into the singularity. But she can receive messages. She just can't send any out. Now I'm picking up the pace here a little bit because I don't want you to miss any of this. And there's a few more pages to go. Now there's a couple of things that could kill her. The one we're going to ignore the actual debris cloud that's around the black hole, but we like to talk about the one that's easiest to describe, and that's spaghettification, which I will show you shortly. And once again, if she's inside and sends a message outward to Bob, it can never get to him. An outward bound message still ends up at the singularity. Depending on the mass of the black hole, she has some time here where she's not dead, but she doesn't have a lot of time. And so Bob just can't keep sending messages, because if he sends a message here, it will hit the singularity after she's disappeared into the singularity. Now, what happens if Bob gets brave and he decides to enter as well? So here's the trajectory of Alice. She deviates from her safe trajectory. She's on curve A. She's going to cross the horizon right here. So they're exchanging messages. She says, I'm going in. And right as she enters the black hole, she sends a message. Now, earlier I told you he will never get this message because it'll take an infinite amount of time for the message to get to him. However, if he's deviated his trajectory, shut off his rocket, and is willing to sacrifice himself, he'll get that message just as he crosses the horizon. Can you see that this light beam emitted by Alice is propagating this weird way in the space-time around the black hole, and he will intercept it right here. So in theory, he can catch that light beam from her, but only if he sacrifices himself. We also agree, there's some more stuff here kind of repetitive. Alice looks like she's slowing down. Bob looks like he's slowing down. Now, what happens if Bob decides to enter the black hole at this place in space-time, not over here, but he enters just after her? He can send a message as he crosses the horizon, and even though she's inside, she can receive that just before she hits the singularity. So the question is, how do we pick a black hole where we do this experiment where they actually both could be inside and survive long enough to communicate to one another and do science experiments, but they won't ever be able to send us the results because any signal they produce goes like this red dotted line, never gets out. So the question is, what happens as we pick the black holes where we do the experiment? So first thing, I've already introduced the term spaghettification. And here's what it's all about. If you're out in space, so this is an easy experiment to do, astronauts have done it. If I have an orange in this hand and an orange in this hand, I let them go, they both fall toward the center of Earth. But they have different positions, so each will have a different trajectory. They actually will move together as they move towards the center of our planet. And this motion of this orange towards this orange is called a tidal force. So the astronaut an astronaut hovering over Earth or a black hole feels a compression because different parts of their body are at different locations and wanting to fall to the center. And there's less gravity at their head and more at their feet. So they get squeezed together by this tidal force, and they get stretched by that tidal force, and they become spaghetti. Hence the technical term, spaghettification. Like this. Now let's talk about survival. And this is serious. People have done this because they know the strength of human tissue and so forth. The mass of the black hole dictates how long you can survive when you fall through the hole. A small black hole is deadly immediately. For example, if you turn our planet into a black hole, it would be about a few centimeters in the horizon, or the Schwarzschild radius would be a few centimeters. If you go near that, you'd be destroyed instantly by tidal force. But if you approach the black hole at the center of our galaxy, which has 4 million solar masses, that's a symbol for a solar mass, the time between crossing the horizon and arriving at the singularity, 60 seconds. And your tissue of your body will hold up for about 9 seconds. So you could actually fall through the horizon and survive some short time. If you go to the biggest black hole in the universe that we've found so far, this number keeps changing all the time, but when I wrote this lecture, 20 billion solar mass black hole exists in a galaxy far, far away. Your falling time from the horizon to the center, over 80 hours, and you could survive for 13 hours and do experiments, but you can never send the results. You undergo this kind of stretching and destruction. So in summary, because I want to save some time for questions, in summary, using Kruskal diagrams, we can explore causality. That is, how do people interact with sending signals by light? What happens to them if we watch them approach the black hole, cross the horizon, and disappear from our universe? And we did the whole thing without any math. Incidentally, I'll say this real quick. If you're interested in this topic and other lectures of this type and can tolerate my lecturing style, you could go to my YouTube channel here. I know that's a lot of stuff to type, or write to me, and I will send you this YouTube channel address, because I have lots and lots of lectures in there of this level of technical content. Also, the University of Denver has an adult education program. You can reach that link here. And I will be teaching a 16-hour lecture series on modern cosmology starting in the winter semester. So you can go to this address and get the catalog and see and sign up. There is a fee for doing this, but so I'm done talking. So I'm wondering if there are questions.
I've got one.
Okay.
So if nothing can escape the event horizon, how can black holes evaporate, and why don't they take the lifetime of the universe to do that?
Okay, so this is, we can't go into it much. I'll just say a few words. So this is Hawking's idea, and it requires introducing quantum mechanics into the description of the black hole. So write to me and I can point you to some very interesting podcasts and non-technical discussion of this issue. But yes, black holes do evaporate. Big ones, the evaporation time is sort of like 10 to the 100th years, not worth talking about. Little black holes evaporate in microseconds. It all depends on their
Ed, you're right. And Peter, I can talk to you about this. I actually understand the Hawking radiation. It has to do with quantum mechanics and the diameter of the Schwarzschild radius.
Right. Okay. Any other questions?
Yeah, please. First, that was a wonderful talk. If I think of the singularity, is it a point or is it an object with the size of sort of the Planck length?
It is an object. Yeah, it's the only sensible dimension at this scale is the Planck length, 10 to the minus 33 centimeters or something. Yeah, so it's the tiniest thing in the universe. I mean, tinier than quarks or subatomic particles. So yeah, it's very small.
Thanks.
And can you comment on the Schwarzschild radius versus the singularity and what a black hole, how it's defined?
Okay, so the Schwarzschild radius depends on the mass of the black hole. And as I said, if you have, for example, the mass of the black hole at the center of our galaxy, I think the Schwarzschild radius is a few light days. It's kind of like the size of the extent of the solar system. No, wait, hang on. No, I'm sorry. I'm talking about the supermassive black hole, the 20 billion. That has so we can introduce a term here that some of you might want to look up, and that's quasars. When quasars, which are quasi-stellar objects, were first found, they was found that their output of energy was stupendously huge, and it changed on a time scale of a few days. And this was mysterious because time scale of change tells us the size of the object emitting the energy. So it couldn't be a galaxy, because a galaxy like the Milky Way is 200,000 light years across. If the whole galaxy tried to cooperate to change its output, which might be detected by some faraway astronomer, they would have to communicate signals across something that's 200,000 light years apart. So there were immediately people realized quasars, which turn out to be energized by stupendously huge black holes, quasars change power output in a matter of a few hours or days. They must be tiny. And the answer is, we now understand, quasars are, the energy for quasars comes from a supermassive black hole. And if it ingests a star or group of stars or stellar binary stars, its output will surge for a short time, and the power output will go up, in a matter of hours or days. So, but the size, the Schwarzschild radius, depends directly on the mass of the object.
It's essentially where the escape velocity would be the speed of light.
That is correct.
Yeah, so I mean, that's just an easy way to think about it. And in the same sense, if I throw a baseball on Earth, it'll fall back down. If you put me far enough away from the center of the Earth, which I'm not planning to do, and I throw a baseball up, then it would escape. And so there's some distance that's there. You could do this for speed of light instead of a hand-thrown baseball from a mass concentrated at a point, and then you just get the Schwarzschild radius.
Yeah, that's right.
Ed, this is Ansel. I got a question. You showed the cones, which have the past and the future, and the speed of light is a 45-degree cone. But then you said once you cross the event horizon, things change. And so is time still vertical and speed?
No. Yeah, thank you, Ansel. Yes, Ansel is asking a good question. I'm trying to navigate back to my slides. You should still be seeing my slides, right?
Yes, thanks.
Okay, so let me jump to one that has the right kind of artwork. Yeah, right here. Yeah, so what Ansel is asking about is, I made the statement that once you're inside the horizon is this green line. Once you're in here, you have a future. It's defined by this cone, but that future includes the singularity. If you, for example, if you were at this point in space-time and you decided to get on a bike and start riding, you're going to move very slowly in space, but you can't avoid colliding with the horizon. It's your future. So yeah, in a sense, time is going up, and your spatial future, time has switched dimensions, and your future includes the dragon's teeth of the singularity.
I think this is a reasonable way to look at it, that the reason you're stuck there is the horizon itself is a 45-degree line. And if one goes back to a little math way back in high school, these are hyperbolas with the 45-degree lines as asymptotes.
Yeah, right. Actually, for the technical people, this map that I've been showing you is a hyperbolic polar coordinate system.
Yeah.
I don't know how many people care about that, but there's just from a technical point of view, we have polar coordinates, and so, well, this is hyperbolic polar coordinates.
I have a question for you, Ed.
Yeah.
You know, in mechanical engineering, two-dimensional representations are always misleading to a certain extent. How does this become three-dimensional, or does two dimensions handle it?
Well, it's very simple, Bruce. If you have a conversation with a cosmologist or astrophysicist about this, when you decide you want to talk about 3 dimensions, then they start doing math, because it's very difficult to draw. Like the drawing I have on the screen right now struggles to show you 2 dimensions of space and 1 of time. But to do it and to have all 4 dimensions in your head at the same time, the normal human cannot do that. So if you, and you'll see there's quotes in books by, say, Brian Greene, who writes about these kinds of things.
Yeah.
When he starts talking about visualization of curvature of the universe and so forth, he said, well, this is the point where the professionals go to the blackboard and start writing equations.
That's where people like you and Harold and John even begin to scratch your head a little bit, I suppose.
Well, yeah, I mean, the math is immensely complex. And that's not even the right term, because that means something else to mathematicians. It's immensely complicated. And this is why the Kruskal diagram is a piece of genius, because we can have a conversation about these topics without having to do any arithmetic. And by the way, Kruskal was not studying relativity. He was interested in plasma physics and making energy out of fusion reactors. But he understood how to do coordinate transformations in this brilliant way. And we have this tool to work with now.
Hey, I gotta say 2 other things about Ed that I forgot in his introduction. He also worked with MITRE, and he was an adjunct professor at the University of Colorado, and he had the unfortunate experience of writing 4 books with me, and our latest was out last January.
Yeah,
last June.
We're both scarred by that experience of writing books together.
And what's the title?
The book is called Photonics Rules of Thumb. So it will be not of interest to anybody unless you're in the optics or fiber optic community or design electro-optic systems. But
Well, I'm going to send out an email that reminds people of the various speakers we've had and what books they've written. I forgot to mention last week that Mark Ketterer wrote Cochrane's Break. He wrote a book, and I think that it'll be interesting to let everybody know what books our people have written.
Sure.
What I'm trying to do is stop sharing my screen, because I have something I can show you real quick. And I know you're going to want to stop pretty soon. Bruce, can you stop my screen sharing? Oh yeah, I got it. Okay, so now I'm here, and I'm going to bring up something that amuses me. If I can find it, and I can't right now.
By the way, it's sort of an interesting thing that when you look at these effects of gravity and time, you need to build it in for GPS, that part of general relativity that comes up is you're enough, the geosynchronous orbits, no, they're not the GPS satellites aren't there. The GPS satellites, I think, are in low Earth orbit. But even there, you are far enough above the surface of the Earth that you need to build this in. And
absolutely.
Yeah, I mean, it's just amazing that.
And, you know, I'm glad you brought that up, because 100 years ago, Einstein produced his papers, and, you know, there were 15 or 20 people interested, and the general public said, in fact, Einstein himself said, this is of no practical value. But when I give this lecture frequently, I point out that without his theory of general relativity, there is no GPS. The orbits, by the way, orbits of GPS, 10,000 kilometers.
So
They're not low Earth orbit. So I now
but they're not geosync either then.
no, they're above geosync. So I've put up a montage of books by Miller and myself. But any other physics questions?
Yeah, I had a question. So, what you're describing today, is this theory generally accepted? Are there many holes they're finding on it? You know, how solid is it?
Well, you mean the Einstein's theory or this description of black holes?
No, Einstein's theory. I think, you know, Newton was good for a number of years, and Einstein's obviously. So,
Okay.
are we seeing the next thing, or is it
Well,
no holes in this?
The answer is literally tens of billions of dollars have been spent exploring the properties of space-time, and there's never been a detection that deviates from Einstein's theory.
Yes, we've been trying to disprove quantum mechanics and relativity for over 100 years, and we've never been able to do a single case.
That is true. Now, there are mysteries and complexities. For example, a year and a half, 2 years ago, it was a big deal. An international group using radio telescopes took a picture of the accretion disk around a black hole. And it was in the news for days and days. It's a phenomenal achievement that took researchers from literally around the world. And the pictures, if you look at the predictions of what we would see, and then look at the actual imagery that was obtained, they're very, very similar. And we don't know everything about the hole that we're looking at in terms of its position in its galaxy and so forth. Well, we do, but here's another example where we know that Einstein was right. There's multiple. Eclipses reveal the deviation of starlight. You can detect as a result of the sun, the deflection by the sun. That matches Einstein. The anomalous orbit of Mercury matches Einstein. GPS proves it every day, and there are many, many other examples. So the answer is, in the fundamental theory that Einstein produced seems to be flawless. What we don't understand is the mechanics of how small black holes form, for example. This is not understood. And I left out another proof of his theory, gravitational waves, which produced a Nobel Prize in 2017.
Yeah.
The prediction of the waveform of merging black holes exactly matches what you would expect. So are we done? We don't know. I mean, we've been very successful with Einstein, with Newton's theory. You know, we can fly to Mars and do all the things we do. Will somebody in the future improve on Einstein? Maybe. But right now,
not seeing any big holes now then, okay.
There are not any big holes now, but there's lots and lots of really challenging questions, and there are probably 30 to 50 PhDs produced every year on the topic of the dynamics of black holes and how they form and how they evaporate and so forth.
Let me just say, Scott, if I was an expert witness on a car crash, I would use Newton's theory. But if I was an expert witness on something in cosmology or something with a spacecraft like GPS, I would have to use Einstein's theory.
Yeah, we all use it every day, because of GPS. Without GPS, I calculated at one time the error growth. If you knew exactly where your house was and you wanted to navigate to the nearest McDonald's, the error growth is about 7 kilometers per hour. So your ability to navigate, even if you knew where you started and you didn't make the clock correction, which is tiny, it's 13 billionths of a second per day. 13 nanoseconds per day is the correction between the clocks on the satellites and the clock in your cell phone.
Let me ask a question. I mean, is it true that we still, though, don't understand how to integrate quantum theory and gravity? That's
Yeah,
one
yeah,
of the,
absolutely. No,
and
very little progress has been made.
and the other, just an observation, the part I find fascinating, I think everyone here knows what the Hubble constant is about the rate of expansion of the universe. And yet we have two numbers now that are really incompatible. I think they're close to a five. The next publication will be a 5 standard deviation difference. I mean, and we really just, I think it's fair to say, don't understand this within standard physics.
Well, let's take this opportunity now because time's moving on. The man who's on the screen right now, Harold Hastings, is going to be doing our talk next week. Can you just give us a brief intro, Harold?
Sure. Well, let me give you a very short intro. I'm going to talk a little bit about network dynamics. There'll be fewer diagrams. There's a phenomenon I want to talk about called cascading failures. Those of us who lived in the Northeast, and I think it was 2003, observed that the lights went out on a Friday afternoon as basically a series of failures propagated through the network too fast to react. And I think there are some analogies in network science between this idea of networks and propagation of failures and for example, the spread of COVID, that if we can't monitor what's happening and react on a time scale faster than the spread, it can spread through the networks of human connection. So I'm going to talk about network science with thoughts of networks like food webs and social networks and ecosystems more generally, power grids and things like this. And interestingly, just the last comment, in power grids, people have talked about sort of local areas and circuit breakers and cutoffs. And you can, I mean, the system is not as modular as it might be, but you can imagine a travel restriction in COVID to prevent the spread of COVID is roughly the same as putting a circuit breaker in a wire connecting two areas where I want to prevent power from being transported to another. So there's this field called network science, which I found enormously exciting when it was first came out in the 70s, and I had a lot of hair. And anyway, we'll talk about some of that and how it works.
Great.
All right. Well, thank you, Ed, for an incredibly well organized, and I almost feel like I understand it, which is never happened before when I've talked about this subject. So this was really fun, and look forward to seeing you all next week. Thank you very much.
Okay.
Thank you, everybody.
I agree, Bruce. It was very exceptional understanding. I learned some things.
Great.
Set the bar really high.
Yeah.
Yeah.
Thanks, Ed.
Those of you that are going to do
Bye.
a talk, don't let Ed intimidate you.
Makes it tough for the rest of us, Bruce.
Well,
Yeah.
that's
Thank
a
you.
good
That
thing.
was really clear.
Okay.